Okay, so this is on, right? Okay, so we can start. So till now we have done nothing. We have just reviewed prob and stat, um, and the idea was that the prob and stat will be needed throughout this course, and you will realize that starting today. Okay, but the actual content of reliability starts from today. Okay, um, so to start with, can you remind me what was reliability? We discussed it in the first lecture, the introductory lecture. What did we define as reliability? When someone said trustworthy and all those things, right? So what is reliability? Correct. Probability that a system will perform satisfactorily throughout its lifetime, and that's the ideal definition of reliability. But often you will see that we will not consider throughout the lifetime. We will consider that it is not changing with time, and that's the idea of time independent reliability. But the idea is that the system is not degrading with time, which is not a realistic scenario. Any system that you can imagine always degrades with time. So when I'm assuming that the system is not degrading with time, that is kind of an assumption, or rather you can imagine that we are only interested in a very short time duration, and in that time duration things are not changing, right? But long story short, in reliability we are primarily interested in computing the probability that it will perform satisfactorily, or if I reverse it, then we'll be interested in finding out the probability of failure. And if I can calculate probability of failure, I'll just subtract it from 1, and that will give me the probability of survival or reliability of the system. Okay, so in reliability, one of the primary goal is to compute the probability of failure. Okay, the goal is often to compute the probability of failure, right? And where is this notion of probability coming into picture? Why is there a chance factor or a probability coming? What is the source of this chance factor? Some uncertainty, but uncertainty in what? Inputs. So this chance factor of the term probability comes into picture because we do acknowledge the fact it is not possible for us to know beforehand everything exactly. For example, it is not possible for us, let's say if there is a car, to predict what is the aerodynamic load that will come on the car exactly. And so the idea is that you will model it as a probability distribution. It is not possible to know the exact boundary condition. You know the exact boundary condition theoretically, but when you do go and perform an experiment, you cannot have a simply supported boundary. For example, you can only approximate at this much distance, and then it will be like simply supported, and so on and so forth. And same material properties. Material property by default is heterogeneous. Materials are heterogeneous, and you are not modeling it as heterogeneous material. So that means there is assumptions coming into picture, and because you cannot remove that assumption, one of the idea is to model things as probabilistic, right? So probability comes into picture because inputs are random. And that is why this notion of probability is coming in the definition or in the objective of a subject known as reliability analysis. That is why this notion of probability is coming into picture, right? But if we go back to the original goal or definition, the goal or definition is that whether a system is performing its desired functionalities or not. Now that's a sentence, but if I have to do it in mathematical way, if I have to write a computer program, I will need the equation, the maths. So how will you know, or how will you write or define mathematically whether a system is performing its desirable functionalities or not? How will you do that? How will you define mathematically whether a system is performing its desired functionalities or not? Range of output, can you give an example? Maybe expand on what you are saying. What do you mean by range of output?
Let's say the case of deflection of beam.
Correct.
Right? So if it is beyond certain range, then it will be called a failure, and within certain range.
Agreed. But again, that's a sentence. Now, how will you make it converted into equation?
So if it's like an AC, then the temperature which is like we're assigning it to cool it down.
Right.
And we're sensing it with the sensor.
So that's another example. But I want an equation. Deviation from the. So it's about failure. Remember that. So it should be deviation from what we consider to be safe, or what is the limiting condition of safe. Right? But you will need to define something. I mean, all of you are correct, but all of you are speaking English and not maths. We need maths. So what is that? That is what I want to quantify. But how will you quantify from your statement? You will need to define a function that tells you about the limiting behavior or the limiting condition of the system you are considering. And I will take the example that you specified, cantilever beam. Okay, and let us try to understand what do I mean by that. Okay, so let me write what we are trying to arrive at, but then we will start with an example. Okay, so this is known as limit state function that we are trying to talk about. Okay, and limit state function is a function that specifies or gives you the limiting behavior of the system. Okay, and that's why the name limiting function. There is another name known as the performance function. We call it performance function because it is also dictating how the system is performing, and that relates directly to the goal, which is to calculate the probability of failure, right? So basically, limit state function, it is a function, and we will generally denote it as g of x, but it can be something else also. Okay, which tells us about the limiting condition. And when I say limiting condition, what does it mean? It means that one side of this function will be safe, the other side of this function will be failure. So this is like the border between safe and failure. Okay, this is also known as the, as I said, performance function. And these two are synonyms, so don't get confused. This is also known as the performance function. Okay, I told you on the first day, I don't care what happened. Okay, so this is known as the performance function. So let us now try to understand it with an example. and I will take the example that you specified, the cantilever beam. Okay, so let us take a cantilever beam. Okay, so this is my cantilever beam, and let's say it is acted upon by a point load P. This is the length, and the length is L, and then there is E and I. E is your elastic modulus, I is your area moment of inertia, P is the point load, L is the length. Okay. So an example limit state function will take the following form. Let us see. L by 325 minus P L cube by 3 EI. Okay, and let us now try to understand and dissect this function. Forget about L by 325. Okay, we'll talk about it separately. First, PL cube by 3 EI. What is that? Deflection, all of you are aware of. Okay, so this is basically deflection. Okay, L by 325. What do you think that is? You were right. What did you say? Limiting condition. So that is the maximum deflection that the beam can withstand. If it goes beyond that, then it will fail, or we will consider it failure. If it is lesser than that, then we are fine. So this is known as the limiting condition. Now one question will come, why L by 325 and not L by 250 or L by 200 or L by 500? Or if I am being more specific, who will give me this limiting condition? Experiments, yes, but those experiments you are not going to perform, you will not have the, how many experiments? First question. You can only perform a limited number of experiments. So generally this is given by what is known as codal provision. So each country has their own codal codes. India has Indian standard codes, IS codes. If you go to US, you will have the American standard codes. British has their British codes, New Zealand has their New Zealand codes. So each country, Europe has its own European codes. So each of these countries have their own codal provisions. And this code specifies what is the maximum deflection until which, and in this case the example is deflection. So what is the maximum deflection until which we will consider it safe? Now how did the code arrive at those numbers? By experiments, you are right. But those codes document those, the government in those countries document those, so that each individual do not have to perform experiments, and there is some standardization that is maintained throughout the country. Otherwise, you will come up with your own limit, someone else will come up with their own limit. And then if something fails, who is responsible? There is no accountability. With these codes, there is accountability. So if a civil engineer is designing something and not following the codes, then they are accountable. If a mechanical engineer is designing something and not following certain guidelines, which is provided by the Indian government, then there is consequence. That engineer is accountable. So this limiting condition you will get mostly from codes, right? Indian standard codes for our case. Or there is one more place from where you can get it, which is the client. You are designing something not for yourself. Most of the times you are designing something for the client. The client can always say that this is the codal provision, I want more safe. A structure that is more safe, a card that is safer. And then in that case you can be more stringent. So this L by 325 can be L by 500, right? It can be. So this number L by 325 is actually for column kind of structure. For normally it is L by 250 from codal provision. So I took that number 325. But long story short, you don't need to remember that. You only need to know that those will either be given to you or you have to find it out from codes. And the codes will specify for a given system what is this limiting condition. I'll give you one more example how this can change. Suppose I am designing a nuclear reactor, okay, and I am designing a normal building, residential building. Now a nuclear reactor has to be much more safer, because if the nuclear reactor fails, we are not talking about a nuclear reactor, we are talking about a city, right? But if a building fails, and it's a residential building, maybe 2-story, 3-story, then it will result in much lesser loss of life. So as a result, this number will be more stringent for a nuclear reactor than a residential complex. Okay. For a hospital also this will be more stringent, because hospital, if there is some failure, no one can escape because they are patient, and there might be lot of loss of lives. Okay. So this is how a limit state function will look like. So a gx is equal to this. So if I put equal to 0, that is my limit state function. Okay. So it's basically a function, and you can understand that if this function is equal to 0, that is my limit state function, my performance function, the limiting condition. If it is greater than 0, then I am safe, right? Because the deflection because of the applied load is less than the allowed. And if it is less than 0, then that's failure. So it is a limit state function that helps us in defining the failure domain. Okay. So we use limit state function to define a failure domain, and failure domain I am going to write it as omega f. Okay, I am going to write it as omega f. And what is omega f? Omega f is equal to all those x. Remember, capital X was the random variable, small x are the realizations of random variable. So all the realizations of capital X corresponding to which your g of x is less than 0. So the failure domain is, okay, it should be omega f, sorry. So the failure domain is all those x corresponding to which the limits there is failure. That is known as the failure domain. Okay. So we have defined limit state function, we have defined failure domain. Any question on these two aspects, limit state function and failure domain? Which is that parameter? Ah, right. True. Correct. In that case, you will have multiple limit state functions. So I'll give you one example. Forget about car. In this case, even stress, bending stress can be a criteria. That bending stress would not be more than a certain criteria. So then I will call it G1x and G2x. And then I will calculate failure or probability of failure because of deflection criteria, probability of failure because of stress criteria. And then these are two individual, and this is known as component reliability. To find the system reliability, which we'll cover much later in the course, maybe after minor, there we'll try to combine this component reliability to come up with the reliability of the system. And that will be the overall reliability of the system. So that is known as system reliability. Now system reliability, you might have multiple limit state, as you mentioned. And obviously this is the easier case. If there are multiple limit state, you can always combine them into a single limit state. Right? I mean, less than 0, and all those things you can come up with. And that's the easier case. The more difficult case is if the system itself is like a system and not a component, like a building. A building is comprises of beams and columns and slabs. A car, it comprises of so many components. Now in that case, if a beam fails, does it mean the building has failed? It need not be. So that means each of the component in this case might have its own probability of failure, and they should combine in some manner to give you the probability of failure of the system. So again, that is the more complex system reliability problem, but what you are saying is also a kind of system reliability problem. Okay, so you will have multiple limit state function and you have to combine them. That's the whole idea.
So, sir, even in one component itself, if the two physics are applied and
Multiphysics.
multiphysics are there, and they are acting together, and both will have effect, and they
True.
will have the limiting function, and both are dependent on each other.
Correct.
That scenario will also.
So by the way, in system reliability, things are dependent on each other. Without things being dependent on each other, then we would just do some easy thing, right? So even in system reliability, whether a beam fails or not, that has an influence on the column. So even in that case, that is. But to take your question in a more refined manner, you are saying that it can be, instead of a beam, it can be a multiphysics problem. If it is a multiphysics problem, there will be multiple physics that is governing. Let's say in this case, there is also heat source I have given. So now that becomes a thermomechanical problem. So it is deforming because of heat and it is deforming because of load. So the ultimate load, the right hand side second term, will be function of both heat source and load. But still, my limit state can still be deformation. But that deformation is now being influenced by multiple physics.
There will be two G of X.
Not necessarily one G of X.
G of X.
If it depends on the criteria, not on the number of physics. So suppose it's a thermomechanical problem. It's a multiphysics problem. But I am saying I am only interested in failure due to deformation. That deformation is multiphysics because it is deforming because of heat and deforming because of load. So it is thermo and mechanical. But I have only one limit state function, which is my deformation allowed deformation minus deformation that the system will undergo. But how much deformation the system will undergo will now come from a multiphysics problem. So that's a multiphysics solver that is sitting there. But your limit state function is a single one because I am only considering the deflection to be the limit state function. Clear? So for multiphysics problem does not necessarily mean you have multiple limit state function. It depends what is the criteria you are setting. Clear?
For that criteria, there will be only single limiting.
Depends. If I also consider stress, then there are two. So nothing is changing because the problem is multiphysics. The only thing that is changing is that how you are calculating deflection. That is the only thing that is changing. If you take stress, there is two. You take bending moment as a criteria, there will be three. And you add one more criteria, that temperature should not be more than that, 4. You can keep on increasing. But that is increasing because what parameters you are looking into to decide whether system has failed or not because the problem is multiphysics. Yeah.
Sir, is it necessary to have only one random variable? Because if we have 2 or 3 parameters.
Do you think there is one random variable?
The capital X.
I'm coming to what is capital X? That was the next thing. You started it. Tell me, what is capital X? What do you think is capital X in this problem? PLEI, everything is capital X. Whatever is random is capital X. So I have not written X on the right hand side, so you must be wondering that what is X this? What is this X? There is no X on the right hand side, right? I wrote it in a generic fashion, that's why I have not written it. But actually you can imagine P as X1, L as X2, E as X3, I as X4. So in this case, this example itself, you can potentially have up to 4 random variables. Okay. Why am I saying potentially have? Because you can always consider no, L is fixed, it does not have variation. Then it is 3 random variable. You can say no, L is varying, but P I know I am applying and I have very good control, so it's not random. So very unlikely, but it can happen. So in that case, okay, clear? So, and that was the next thing I was coming into, that this X that you are seeing here, these are the random variables. And in this example, you can have up to 4 random variables. Okay. So in the example considered, X is equal to E I L P. Okay, so 4. And this is a very important point, by the way. In mechanics, in civil engineering, in mechanical engineering, in all of these things, we deal with maximum 4 dimensions, x, y, z and t. You do not deal with more than 4 dimensions. But when the system becomes stochastic, we consider 4, 5 dimension to be low dimensional. Your dimension can be in the order of 100 to 1000. So for a system, you might have thousands of random variables. And I will give you an example, very simple example. Let's think about Burj Khalifa, the tallest building in the world. Wind force is there, which is random and all those things. And not only that, I don't know the number of stories, but let's assume that it is 800 feet or something like that, right? So let's say if I consider 3, so 200 story, 250 stories maybe. So there are 250 stories, let's assume. Each story will have how many columns and how many beams? You do not know, but let's say each story has, just as an example, 10, which is a very less number, it will be more. So each story has 10 columns and 10 beams, 20. So, and then how many? I said 200. What is the number of random variable? If all of these are random, 200 times 20. So you can imagine that in this reliability analysis or uncertainty quantification kind of problem, you can easily go into the range of 1000 dimensional variables. And 1000 is very common. Okay. So dimension here is not 3 or 4. And that is why one of the major problem in this kind of in this domain is what is known as the curse of dimensionality. So as the dimension increases, most of the method starts failing. There is only one method that is independent of dimension, and that is the Monte Carlo integration or the Monte Carlo simulation, which we'll talk later. Okay, but this dimension is, take a note of that the dimension can be very high. So this is a, you can understand, right? This is a very small dimensional problem. And I will add one more layer of complexity here.
Like you were saying that P is not usually a random variable.
No, P is usually a random variable. I assumed that. I said that will usually not happen, that P is not a random. If anything is a random, that should be P. I mean, that's the most sensitive one.
That is what I was thinking, that if P is fixed, then I is a stochastic method, then it will become more like a.
Yeah, no, E and I can still be random. Even if one is random, the overall thing is random, but
So the same material is a
yes,
same material and
same material, same system. It is random. So by the way, and this is the important, this randomness comes into picture because we are not able to estimate it exactly. First thing, keep that in mind. So if it is E, you will not be able to estimate E at all the points. So it's better to assume it as a random, so in that sense, okay. So always remember this, things are we consider random because we cannot estimate them exactly, and that's the source of it. If I can estimate what is the wind speed on an hourly basis exactly, then wind load is no longer random. So it's random because of our limitation, not because the system itself is random. The only thing that is truly random is, there is only one thing that is truly random, quantum. Quantum by definition, everything is random, okay. But then you can always argue that maybe we have not developed that theory which will make quantum deterministic. I mean, I can always argue that, right? So yeah. In the example, yeah. So these are the 4 random variables we have considered, okay. So now let us try to formalize it, okay. So we have defined Gx, and in our example we wrote Gx as L by 325 minus PL cube by 3EI, okay. But this is for a given example. In general, what is this L by 325? Maximum allowed deformation or deflection of a cantilever beam. So if I take cantilever beam, I can extend it to system, generalize it, and then this becomes the maximum allowed something, right? That is like the capacity of the system. Okay, so I will call it as capacity C. Agreed? Capacity, you understand? What is PL cube by 3I? That is the deflection that is coming because of the applied load and material property and boundary condition, right? So that is like what is That is more like a demand. Because of this thing, this is happening, and this is for this I would like to keep it safe. So that is the response, but we can also think of it like the demand in economics kind of terminology. Okay. So then my limit state function is represented as the difference between capacity and demand. Okay. And obviously capacity will also be function of x, demand will also be function of x, but it is not necessary that capacity will be function of all the x. Like in our example, capacity is only function of L, whereas demand is function of all the x, but that is also not necessary. Demand can also be function of some of the x. Okay. Demand can also be function of some of the x. So keep that in mind, that it is not necessary that every random variable will influence your capacity, and similarly it is not necessary that each and every random variable will influence your demand. Okay. So this is the capacity and demand way of looking into reliability. Okay. Now remember that C and D are function of x. So C and D in a generic sense is also random, because x is random. So this is my capacity, this is my demand, and both C and D are random, and if they are random, they will have a probability distribution of its own. Let's call it as FCC and FDD. Okay. So this I will refer as F capital C, C, and this I will refer as F capital D, D. Okay. Nothing difficult, simple. Just some notation I am bringing into picture. Okay. So now let us try and plot this capacity and demand PDFs. Okay. So this is my C comma D, and this is my FC comma FD.
So what was small d and small c?
Realization samples. So capital C is the random variable. So if you take a sample of that, so always remember capital X, capital is the random variable, small are the realization of the random variable. Okay. This is FC and FD. So for a moment, okay. So let's say this two PDFs looks like this, where this is my FD D and this is my FC C. Okay. What do you think is the probability of failure if this is my PDF? Remember, probability of failure is when C is less than D. Area under the curve, basically intersection curve, right? So the probability of failure is this area. I mean, obviously this can extend, but basically area under the two curves, the common area under the two curves, that will give you the probability of failure. If you want to understand it better, assume that C is constant. If C is constant, how will the PDF looks like? It will be a straight line at that point, direct delta function. So if C is constant, just to explain it and give you some intuition, if C is constant and let's say that is the value of C, then everything that is on the right hand side would have been failure, right? Because C is probabilistic, it also has a PDF of its own, and then you are looking at the area under the curve. Okay. So this is how you can compute. If you can compute this area under the curve, you can compute the probability of failure. Keep in mind, you will never be able to compute this, because who will tell you what is the probability of capacity and demand? Okay, capacity I might give you, demand, how will you know the probability? You might know the probability of P, L, E and I, but now there is a nonlinearity L cube sitting. You will not know this. So this is only for understanding. In practice, you will not be able to use this, but this will help you develop the understanding, which will help you take it to a practical forum or practical platform where you will do something else. But this understanding will help you understand what you are doing in the practical sense. Okay, so keep that in mind, because FC and FD you will not know. You will not know. Okay. How we got the area? So first think about that. This is constant. C is constant. If C is constant, it will be that violet line you see. So in that case, what is the probability? It is probability that D is greater than C. That will be integration of FDD, which is the PDF, in C to infinite. Correct? C to infinite. That will be your probability of failure. But in this case, your C is also random. Because C is random, what is happening is I am just extending it. See, if this was the case, I would have taken this, and whatever is the area here would have been my probability of failure. Now, because this is random, I need to also account for that. So that PDF is coming here, and then I am saying it is the basically area under the curve. If those two are far apart, then the probability will reduce, and if they are very close, the probability will increase. Okay. He asked first, you had some question, then I'll come to you.
Sir, at the intersection, so to the right of the intersection, FC is always greater than FD.
Correct.
So how is that area under the curve?
What is FC? PDF, it has nothing to do with the value.
So
It's a probability, remember that.
yeah, so that is conceptual. Even in that case, sir, suppose that we take to the right where the FD curve is ending and we take those areas, then also the FC area will be greater than the FD area.
It can be.
Right.
Think about it. You are getting confused, and I understand that's a very common confusion, because you are thinking of it from a stress strain curve, where you compute the area under it to get the energy and all those things. Here it is not stress strain curve. Here y-axis is what? It's a density. It is saying what is the chance or sum that this value will observe. The value of C and D is only in the x-axis. In y-axis is the probability. So it is just saying that at this point, the chances that C will be greater than D is very less. That's all. But it can still be less, because you have to think in a probabilistic manner. Okay. So what will happen is that the area will reduce. That's all. So if you go here, in this area FC, the frequency is very less, much lower than the frequency of FD. That means you will get many D's here, but very few C here. That's all that it means.
But to the right of intersection, the chances of C being greater than D is higher.
Correct.
So why are we saying that that is a probability of failure?
Repeat again.
In the right at the point where the two curves are intersecting.
This one.
This point.
Yes.
The probability of C being greater. Wait. Yeah. So this is like at this point we have a fixed C comma D.
Correct.
And for the probability of this C occurring is higher than the probability of D occurring.
Here is a catch here. Let me explain. This value, although I told him that is probability, what is it actually? It's the density.
Yeah.
Density is not probability.
I mean, if we take like a sliver.
Correct. I'm coming to that. So what is, even in that case it will come, but that is some representation of dense. If I find the ratio of these 2 points, I can say that here the points will be there with less chance. Okay. But coming to your main question, at this point, the chances of, this is for D. So the chances of D being greater than C is less, but that is not zero. That's a finite chance that is still there.
So, can explain again how you are figuring out the problem, the area where we have probability of failure.
Correct.
Why did you take the area in between?
Correct. So let's, as I said, let us start with the easier one, and this is very important. So I can spend the rest of the lecture on this also. So this is PDF of D. Okay. This is my C. So what will be the probability of failure? This is my C when I'm saying, remember this is not my C. This value is my C. Don't confuse with the line. The line I'm drawing to just denote that point. But this point is the C.
Anything on right on this would be failure.
Will be failure, right? Let's take another curve. Now it's opposite. This is my C. Okay. This is my D. Then this is D and this is C. Then what is left? Now let's combine that. The previous one was, by the way, something like this. And in this case, we were saying this side. In this case, we were saying this side.
No, wait, in the first curve, C, it should be the right of curve.
Which one?
C minus D should be greater than 0.
In this case,
Probability of failure is left of.
failure. I'm only talking about failure. Okay. So in this case, you are looking at this area, right? In this case, you are looking at this area. This is the previous case, by the way. So in this case, this was FD and this was your small c, right? So now you combine the two curves. And now try to figure out what is happening. What you will do, you will ideally take, this is my D, everything left of D.
Which one is FD, which one is FC?
This is FD, this is FC. So with FD, this is, I should take whatever is there. And with this one, I should take whatever is there when I combine these two. So we'll end up with that. And by the way, don't think only this area, by the way. If this goes like this and this goes like this, I will have to take the whole area, by the way, whatever is non-zero.
Can you show the mathematical?
I will come to that. That is the next thing. So I'm coming to that. Yeah. Yes, I'm coming to that. We'll do a mathematical derivation of this. Okay.
We're saying that the probability of C and D is same. Is that what we're saying?
At the intersection of the whole curve, what do you mean by that?
The-
The way the points are cutting.
Yes, on the
We are not saying that. We are saying the frequency is same or the density is same. That need not be probability, by the way. Okay. Because in this case, I have drawn both to be symmetric. It is not true that both will be symmetric. You can imagine that C is log normal or the other one is not. In that case, even if you take a small area, the area will not be same. So it looks like that because I have drawn them to be Gaussian in some cases. Yeah, so let us pause here and please give it a thought that what is happening. In the meantime, let me draw it in a better manner maybe. This is my FCC. So this is the probability density function of the capacity. And let's assume something that is demand and let's call it small d. Okay. And if this is the case, we know that as long as capacity is less than d, that is a failure. So in this case, I will do integration minus infinite to d FCC DC, and that will give me my failure, right? That is what I will do. The other case is this is now my FDD and this straight line is my capacity. Okay. This straight line is my capacity, small c. So in this case, my probability of failure will be integration c to infinite FDD dd. Are these two expressions clear to you or not? R2 this expression is clear to you or not? If there is any question, please ask. Okay. The combination I am coming in a short while, but forget about the combination. Think about a deterministic case where either C is deterministic or D is deterministic. In that case, this is making sense or not? And always keep in mind that y-axis is your density, not your some value. So that is very important. Otherwise, you will try comparing the y-axis height. That you should not do. That will happen in the mind. So y-axis is your density. It has nothing to do with the value. It is just telling you what is the probability of that value. So don't compare the y-axis height. And just think of it from an integration point of view, the two integrals. Is it not giving the scenario where C is less than D? Both the integrals. Right? Clear? So now, if I have to combine them, what will I do? I will do the following. See, I will select a C and I will select that C with certain probability. And for that selected C, I will find out this integral and then I will integrate over that whole C. Right? What will I do? I will select a C and I will select the C with certain probability. And then for that C, I will integrate D. And that should give me the probability of failure for that point. Now, if I want, I can now integrate over C also so that it will cover all the values of C. Clear? So let us try to write it down. So let's write D of R. What is D of R? Not probability of failure, but probability of reliability, or the reliability basically I am writing. I can find out the other one by just one subtracting. Okay. So for D of R, what we'll do is as follow. First, consider FCC. Okay. And from that FCC, let us take a point C. Okay. And because a point do not have a probability, so we'll take a very small strip. Okay. In fact, let me do one thing. Let us try with D. Let us do it for demand. I can do it either, doesn't matter. Okay. Okay. So what is the probability that D will be in? D minus dd by 2 comma D plus dd by 2. What is this probability equal to? But it's a small d, so I'll just calculate the area. So this is equal to f dd multiplied, so this is my height, multiplied by dd. Right? Now dd is might slight confusing, but since I'm using demand, so I'm using this dd. That is basically the usual thing we do in all integral, right? So this is the chance with which I will select D, which is my demand, in the small range. Correct? Given that I have selected it, then, so this is the probability with which I am selecting it in the small range. Okay? Now, given that I have selected this D,
So DD is like
small d, yeah. So given that I have selected this small d, okay, what is the probability of failure now for that given D? Capacity, and capacity should be less than the selected D. So minus infinite to d. Because if capacity is less than the selected demand, then it will fail, but I am talking about reliability. So it should be opposite. I am not talking about failure. Look at it. I have talked about that would have been the case if I was talking about success. D d to infinity. Yeah. So I'll repeat. Please stop me if you are not following. dr is a small reliability I am trying to find out, which I'll ultimately integrate out, you can understand. Now for finding out this small reliability, first I am saying that the demand has a PDF. What is the probability with which it will take a small value d and in a small range? And that is the first area that you are seeing, which is FDD DD. That is the probability with which you are selecting this d value. Now, given that you have selected the d value, what is the chance of survival? What is the reliability? So the system will only be reliable if your capacity is more than that selected d. So if I consider the PDF of capacity, it is the area towards the right of that. And that is why it is going from d to infinite. So this is my PDF, the reliability of that small d value. But I am not interested in that small d value. I am interested in the all values of d. So then what is capital R? Capital R. I should integrate over d as well. And in theory, d can go from minus infinite to plus infinite. Right? This is my reliability. What is probability of failure? 1 minus r. So I'll write that, but can you give me an expression? Without, so I'm not doing 1 minus r, I'm just writing it because it is 1 minus r without a doubt. But let me write some expression and you tell me if this is correct or wrong. FDD capital FC D DD. Tell me if this is correct or wrong. What is capital FC? CDF. So now you think. What will change for the failure case? Selection of D. Tapas, come and sit. So what will change in the case of probability of failure? Selection of D will remain as it is, but the second integral will be now in the minus infinite to D, and minus infinite to D, that integral is your CDF. So you get this thing. Okay. So this is your probability of failure, which will basically give you what we are saying, the area under the curve. Okay. What is CDF? Read probability and statistics if that is the question. CDF is defined as integration of minus infinite to a value PDF D. So that is the CDF.
So if we just change the limit from minus infinity to d, it will be failure.
What?
The first line, if we just change the limit from
minus infinite, correct. That is the failure. Exactly. That's the final expression. Exactly. Clear? So please go through this. We have a next lecture day after tomorrow, right? So I'll start with this and then we'll do some special cases, which is where the variables are Gaussian, C and D, when the variables are log normal. And then you will realize it is useless. And so you will need more better methods, advanced methods. Okay. So that is what you will realize ultimately. Okay. Thank you.